So I want to teach you a little bit about energy in springs, because obviously why would we talk about force in springs if we weren't going to then talk about energy in a unit that's called energy, right? So here is the problem that you have when you try to come up with the formula for the energy stored in a spring in terms of the stiffness of the spring and how much you've stretched it. Here is the problem, okay? And that is that if we look at a graph of F versus X, like this, and we stretch the spring some distance X, okay? And we want to figure out the energy stored in the spring. We would use the formula work is F times S, yes? Can we stop? Yeah, thanks. Okay, we're going to go work is F times S, right? Well, S is easy. I stretched it some distance X. That's the easy thing, right? So I'm going to put X in there for S. But what should we put in for the force? Should we put in the 0 that we start at? Should we put in the Kx, F equals Kx, that we end with? Or do you suppose it would be a good thing to put in here the average force that we exerted? What do you suppose is the best thing to put in there? Let's put in the average force, because it's not too much, and it's not too little, right? It's just right, yeah? Okay? I didn't want to lead you. See, some teachers in this situation would try to lead you to the right answer. I like how it just kind of sprang from your minds, right? You know? Okay. So for the force, I'm going to put 1/2 kx. Yeah? Guys, please stop. For the force, I'm going to put in 1/2 kx. For the x, I'm going to put in, or the s, I'm going to put in x. And of course, this ends up being that the energy is 1/2 kx squared. And since it's not in your data pack, I'm just going to call it a big P. It's the potential energy. It's a different kind of potential energy than gravitational potential energy, right? The 1/2 kx squared. And there's a lot of things, by the way, like when you store energy on a capacitor, these are these things that store charge. So like for camera flashes, right? That's why they have to charge up. It's like bzzz, right? And it charges and charges and charges, and then it goes flash when you press the button. When you store energy on a capacitor, at first you put the electrons in, and they're easy to put in there because there's no electrons there to begin with. But near the end, it's hard to put the last electron on there because there's so many in the capacitor already, right? And so capacitors, the formula for the energy in them is 1/2 CV squared. Okay, I think. I haven't taught it for a while, right? It's the same sort of thing because it's a linear thing. Anybody here know how to do a antiderivative? Not yet. We don't have those people in here. Okay. Sometimes there is, and I can show you that it is the antiderivative of Kx. Okay. Can anybody do a derivative? Can't. Okay, that's right. I'm not going to go there. But I will show you this, that in general, when you calculate work, okay, in general, when you calculate work and you have force times distance, and I exert a force times a distance, work is always the area under a graph like this. And if the force doesn't change, it's just a rectangle, yes? And the area under is just F times S, which is what work is, okay? Here it's still the area under this graph, right? It's still all this area, and this area is 1/2 base times height, which is 1/2 x, right? The base is x, and the height is kx, yeah? Doesn't that work? 1/2 x kx is 1/2 kx squared. I think it still is, yeah. There we go, right? So, yeah, there we have it. And the reason that that gives you the area is that we can take this little chunk, fill it in there, right? Kind of a thing, right? Okay. Yay. Look how fast you're learning. You guys are so fast. Should we want to try that? You guys want to try that? Let's try that. Whiteboard.